Hi, everyone, and thank you for attending this Snowday session. Whether you're already working with Snowflake or just getting started, today you'll hear some new announcements for how you can use Snowflake to build your architecture pattern of choice. I'm Scott Teal. I'm on the product marketing team, and I'm joined today by these wonderful product leaders who cover many different areas of Snowflake and have lots of great news to share with you. So here's how today's going to go. In this session, you'll hear how the Snowflake Data Cloud is helping customers build many different architecture patterns along with new product announcements supporting each of these areas. Without further ado, let's dive in. Various architecture patterns emerged over the years, each purpose-built for different priorities and use cases. Back in the 1980s, data warehousing emerged as the storage pattern for supporting organization-wide analytics on structured tables. Then in the late 2000s, data lakes emerged as the pattern to accommodate a large volume and variety of data. In more recent years, the data lakehouse emerged to try to combine the benefits of scalability and flexibility of data lakes with the governance, schema enforcement, and transactional properties of data warehouses. In the last few years, data mesh has been an increasingly popular pattern to overcome the bottlenecks of centralized data management. And it's you who's left to decide, which do I need? Most platforms are optimized to serve just one of these patterns, but there's no one-size-fits-all architecture pattern across entire industries, let alone within a single organization or business. So how does this apply to Snowflake? Well, here's a representation of the Snowflake platform. And made up of these various layers of storage, compute, cloud services, and the cross-cloud layer we call SnowGrid. With these pieces, customers build their architecture pattern of choice. Snowflake was founded to solve for needs that the data warehouse and data lakes tried to solve but fell short. And we've continued to innovate and evolve where customers are using Snowflake for more recent architecture patterns like data lakehouse and data mesh. The beauty of this is that since Snowflake is delivered as a fully managed service, your data lake or data warehouse doesn't have to be siloed away. Whether you need to collaborate within your organization globally or across many organizations, each of these teams can build their architecture that fits their use case, yet all be able to securely connect to one another, sharing and receiving data, applications, and even monetizing those assets. Now, for the remainder of this session, you'll hear a bit more about new features and how they support customers implementing these various architecture patterns all in the Data Cloud. Let's start with the Data Lakehouse. As I said before, the Lakehouse architecture emerged to combine the scalability and flexibility benefits of data lakes with the governance, schema enforcement, and transactional properties that were common in data warehouses. From the start, the Snowflake platform has been delivered as a service with those three layers: storage, compute, and cloud services. Our table storage, since we first launched, is actually a fully managed table format implemented on top of cloud object storage, similar to what many people may know today and from open source like Apache Iceberg, Apache Hudi, and Delta Lake. And because Snowflake's table format is fully managed, features like encryption, transactional consistency, versioning, time travel are all delivered automatically. And now with support for Iceberg tables, customers can pick on a team or use case level which storage format and location is the better fit. Some teams or organizations prefer to not have to manage their own table storage and prioritize the simplicity of a fully managed table format, while other teams may prefer to take on more of that management work in exchange for the ability to keep data stored in an open format for more interoperability. So with that, now I'm going to pass it over to Ron to dive deeper into Iceberg tables. Take it away, Ron.
Thanks, Scott. Hello, everybody. My name is Ron Ortloff. I'm a product manager here at Snowflake, and I'm going to be talking about Iceberg tables today. Iceberg tables are a single table type that bring the easy management and great performance of Snowflake to data stored externally in an open source Apache Iceberg format. I'm happy to announce today that we are putting into public preview our Iceberg table offering coming soon. Catalogs are a concept in the Apache Iceberg project that keep track of table metadata and manage a collection of tables. There's are lots of catalog options supported within the Iceberg project. With the Iceberg table offering in Snowflake, you can use Snowflake as your Iceberg catalog. You can also choose to integrate with an external Iceberg catalog as well. We've contributed to the Apache Iceberg project an SDK that allows for Apache Spark to access the Snowflake managed Iceberg tables. We're also working on support for the Apache Iceberg REST API spec. This will expand the number of engines and catalogs that we can support for connecting to Snowflake managed Iceberg tables, or to the catalogs that we can externally connect to and consume Iceberg data from those catalogs. Let's take a quick look at how these catalog options are different. For Snowflake managed Iceberg tables, a quick walkthrough on how those work. So you're going to create an Iceberg table inside of Snowflake using a create Iceberg table DDL syntax. You can then ingest data into a Snowflake warehouse. The external volume that was created as part of the Iceberg table definition is that configuration that allows Snowflake to talk to your storage account and write Apache Parquet as well as the Iceberg metadata to that location. The Iceberg metadata snapshots are registered in the Snowflake Iceberg catalog. The metadata itself is also written to the customer storage account as well. When it comes to consuming the data, data is queried through a Snowflake warehouse to your dashboards and analytical solution, or you can also use the SDK APIs and connect to the Snowflake Iceberg catalog. So here we have Spark connecting to the Snowflake Iceberg catalog. Metadata and data are both read directly from the storage account and then served to your analytical solution. With externally managed tables, something else is writing that Parquet data, some other engine is generating that Iceberg metadata. So in this case, we have Apache Spark writing data, writing metadata to a cloud storage account. There is an external catalog implementation that Spark is using. Those metadata snapshots can be consumed through the catalog integration object that is configured in your Snowflake instance. So with the catalog integration, we understand then how to access the Iceberg metadata snapshots, and then we can use the external volume to read the Parquet data from disk. With the table then configured inside of Snowflake and accessing the metadata snapshots and the Parquet data, the data is then queryable through an Iceberg table in a Snowflake warehouse and can be connected to your downstream reporting solution. We also have the ability to convert an unmanaged Iceberg table that has an external catalog configuration to a Snowflake catalog configuration. So in this situation, you have Spark, like we saw before, a third-party external catalog that's keeping track of your Iceberg metadata. Then you have an external access to the storage account to consume the metadata and the Parquet data that's there. So once this configuration is set up, you can specify an alter table syntax. This is a metadata operation that transfers the ownership to the Snowflake catalog and allows you to be able to write data to that Iceberg table. Snowflake now takes over lifecycle management of that data. You can ingest data through a warehouse, and you can continue to query that data in place as you did before. As new data is loaded, new snapshots and new Parquet data will be written to the cloud storage account. If you want to query the entire life cycle of that table, we'll use the existing data that was there prior to the conversion to the Snowflake managed table. So let's see this in action. Let's take a look at a demo and see how all these pieces can come together. So what we'll see in the demo is we'll start off with a Jupyter notebook that's connected to an EMR cluster. There's going to be some data and some tables that are preloaded and referenced through the AWS Glue catalog. We'll create a table inside of Snowflake, an Iceberg table inside of Snowflake that is using the AWS Glue configuration information to read data from S3. We'll convert that table to a Snowflake managed Iceberg table using Snowflake as the catalog. And then we'll see how the Jupyter Notebook can then connect to that SDK and consume the data that's been modified by Snowflake. Okay, so here I am in a Jupyter Notebook. I'm going to start off by connecting to the Glue catalog. And then within the Glue catalog, I'm going to go into the Iceberg demo workspace. I've got a couple lines here that we'll come back to a little bit later on in the demo, and I'm going to jump down here and run this show tables command. So show tables is going to reach out to the Glue catalog and then bring back the tables that are listed in the catalog. So here we see catalog sales, a staging table, another date table, and a store sales table. So now we see we've been able to browse these tables from the notebook. We will then move over to Snowflake and create these as unmanaged Iceberg tables. Okay, so here we are in a Snowflake worksheet. I'm going to create these Snowflake Iceberg tables that are referencing the external catalog. So the first step in creating the Iceberg table is to specify an external volume. So I'll go ahead and run this, specifying a storage provider, the role information, as well as the location information for the table. Because we're referencing externally managed Iceberg tables, I'm going to set the allow writes parameter to false. This tells Snowflake it cannot write to that storage location. Then I will configure the catalog. So this catalog integration is going to specify Glue as the catalog source, a namespace within that Glue catalog, the table format, as well as the role and ID of the catalog. So with these two things created now, I have an established connection to the storage location. I also have another connection established to the catalog location. Now I can create tables inside of Snowflake. So I'll create the catalog sales table, the date dimension table. We can create these all in one shot. So what's happening now is Snowflake is reaching out to the catalog, understanding what the current metadata snapshot is, looking at that Iceberg metadata, looking at those Parquet files, and then building that metadata information for Snowflake to reference. Okay, so those tables are now created. Now we can go ahead and run a query. So this query, we'll run this in a few different locations and a few different times. So a real quick description of the query. It does a subquery with the catalog sales and rolls up by the date dimension. Then it does the same thing with the store sales table, rolls it up by the date as well, and then it combines the results together. So I'll go ahead and run this here. So what's happening here then is Snowflake is connecting to Glue, pulling in the information, and then querying the table. Okay, so the results are back. We have data loaded through 528. I can also connect a dashboard to this data as well. So here I've got a dashboard configuration that's already defined, some information on details of sales, month-over-month sales as well. So this dashboard has been refreshed. You can see I have data here as well through May 28th. Underneath the covers, we can see that we're also accessing the same query that we looked at before, and just giving it a good presentation layer to view on top of. So now with the tables created inside of Snowflake, we can go back to the notebook. We can insert some more data into that catalog sales table. So here I have some data in a staging table. We'll insert another day's worth of data, and then that's when the catalog sales table will be updated. So what's happening here is we're inserting more data into the catalog sales table. Spark is writing the Parquet data out to the cloud storage account, and then a new Iceberg metadata snapshot will be generated. Okay, so that's done. We can run that same query that we did before inside of Snowflake, as well as in the dashboard, and take a look at those results here. So again, this is the exact same query, the roll-up of catalog sales and store sales by date, and then combining those results together. Okay, so here we have catalog sales and store sales through May 29th. We can go back to Snowflake now, and we can refresh that catalog sales table. So what this alter Iceberg table statement does is, again, reaches back out to Glue and gets the current metadata snapshot and processes the metadata information into Snowflake. When that's done, then I can rerun my query and see new results up to the 29th now, stored inside of Snowflake. I can go back to our dashboard, refresh this, see also data stored through the 29th. So with that done, now we can move into the next part of the demo where we talk about converting an externally managed Iceberg table to a Snowflake managed Iceberg table. So what's going to happen with the conversion, like we talked about before, is there's an external catalog that is writing the Parquet data, that's generating the Iceberg metadata as well. That responsibility now transfers to Snowflake. Snowflake becomes the Iceberg catalog. Snowflake is able to read and write to that Iceberg table. So similar here inside of Snowflake, we'll try to insert a new day's worth of data. I have a catalog sales stage table. We'll try to insert into that table. We see that it fails, which is expected. Okay, we're inserting into an externally managed table. This table is read-only. Okay, so we can attempt to run the conversion syntax, and as expected, this also fails because the volume that I created it on is not writable. So if we scroll back up to the top, we see that we had this allow writes set to false. So that is expected to fail if we want to convert that to a read-write managed table. So I can scroll back down. I can run this alter of the external volume to set allow writes equal to true. The volume is now writable from Snowflake. I can convert the tables all in one shot here. So this is alter Iceberg table, the specific table that I want to convert, and then the convert to managed. I'm leaving the tables. Any future writes will go to wherever I specify in the base location. I'm keeping that the same. If I wanted Snowflake to write to a new location, I could specify that here. So now I can insert data. So this is going to insert new data into that catalog sales table. Again, this insert is putting more Parquet data onto the same S3 bucket location, and it's pulling that data out of a stage table that I had here as well. We can generate the Iceberg metadata, and then we can go back to our dashboard, and we should see new data has been loaded. There we go. Okay, so up to May 30th has been loaded. Now we can go back to the notebook that we had from before, and we can configure that to point that to the Snowflake catalog. So the lines that I skipped before, we can run those now. I can set the current catalog to the Snowflake catalog implementation. This is going to use the Snowflake Iceberg SDK that's part of the Apache Iceberg project. So the catalog has now been set. I can change the namespace, and then I can browse the tables. So this is now using the same catalog API and connecting to the Snowflake catalog and returning the tables that you have access to. So there we see the 3 tables that we've been working with. Now you can imagine if you had a large notebook with lots of different queries in it, you can keep all of those queries just the same that you had from before because the table names have stayed the same. I could come back down here and rerun this query again without making any code changes. And now what we have happening is the notebook and Spark are reaching out to Snowflake, to the Snowflake catalog, understanding what the current metadata snapshot is, reading those Parquet files, and then processing the data inside of Spark. There is no data flowing through a Snowflake warehouse at this point. It is just going from the cloud storage account through Spark back to the notebook here. So what we see then is with the query finished, and there we go. We have data loaded through May 30th, and we have the roll-ups by catalog sales and store sales inside the notebook. So just to recap what we saw here, we started off with the Glue catalog, have our EMR Spark cluster running, a Jupyter notebook connected to that Spark catalog, connected to the Glue catalog, using that same configuration, then creating externally managed Snowflake Iceberg tables, querying those tables, going back to the notebook, seeing the Jupyter notebook update those Iceberg tables. Changes are reflected in Snowflake, changes are reflected in the dashboard that I created. We then went and converted those externally managed Iceberg tables to Snowflake catalog managed tables, made modifications in Snowflake, and then saw those changes reflected in both the dashboard as well as the Jupyter notebook without making any changes to any queries at all. So with that, thank you very much.
Hey everyone, I am Bhanu Prakash. I am a product manager at Snowflake and I work on Snowpark. Today, I'm going to talk about data lakes. As Scott mentioned in the intro, data lakes are a popular storage pattern to retain the flexibility for querying and processing data like JSON, XML, PDF, images, and whatnot. So let's check out how Snowflake supports this pattern and what new features are available for data lakes. Now, whether the files are stored in Snowflake internal stage or an external object store, Snowflake can query these files in place using schema on read and process them in multiple languages like Python, Java, Scala, with the simplicity of the underlying single multi-cluster compute engine. And now let's talk about what are the new capabilities for semi-structured data as well as unstructured data processing. So let's start with semi-structured first. Soon in public preview, you can assign data types to elements in arrays, objects, and map to better enforce schema. You can also automatically detect schema of Parquet, Avro, and ORC files in stage. While this was already available, we are now enhancing it and making it available for CSV and JSON files. And last but not the least, as the schema of semi-structured data tends to evolve over time, systems that generate semi-structured data add new columns to accommodate this additional information. And as part of this, the downstream tables have to accommodate and evolve accordingly. And to better support this, we have added support for table schema evolution. And as we announced in the summit with Snowpark, we added the capability to process files in a dynamic manner, where we announced the GA for Java and then public preview for file processing capability for Python and Scala. Now I'm excited to share this capability is generally available for Python and Scala, where you can securely and in a dynamic manner process files that enables unstructured data processing. Lastly, you can now reach internet endpoints from Snowflake without any infrastructural setup. This enables a lot of use cases. In context of data lakes, it enables you to do data ingestion, data enrichment, and also integrate with a lot of other services and create pipelines. I'm excited to share that ability to reach external endpoints through external access, which has been already in public preview for AWS, is going to be in public preview for Azure soon. Now, let's check this out in action. I'm going to do a quick demo of processing unstructured data using Snowpark and creating an end-to-end pipeline. As part of this, I'm going to do three things. First, I'm going to create tasks and streams to orchestrate the data pipeline that processes unstructured data files. Second, I'm going to create a user-defined function written in Python that's going to read and process the files programmatically. And then third, I'm going to send notification to Slack as part of the pipeline completion, whether success or failure. And as part of this, I'm going to use Snowpark external access that I just talked about. So let's see this in action. So right now, what you see on my screen is a PDF form that has a last name, first name, which product you would like to review. Would you like to recommend this product and the purchase date? Now, this is an example of an unstructured file where the information is available in a PDF form. Imagine you having thousands of files like this, where you want to just run a simple query, like which product did the user review. If it is available in a structured table, then it would be as simple as running a SQL query. So as part of this demo, what I'm going to do is I'm going to upload these PDF files in a stage, and then use Snowpark to access these files from the stage, process it, and then insert into a table. So this screen that you're seeing is all the PDF files that I have uploaded to the stage. Now let's go to my Snow site, where I have created a stream that will capture new files as they arrive. And then I have created this Python function written here, which is using the OSS packages that are available from the curated experience of Snowflake Anaconda channel. And then I'm using this Snowflake file class, where I'm using snowflake file.open to read a file from the stage, and then processing the file and then returning the results back. So let's see one example of what it would look like to call a function that processes a file. In this case, I'm going to run this SQL query, where as part of the select, I'm calling PDF_parse and giving scoped access of the file to this function to extract the information from PDF. So here I ran and I got this result in a semi-structured form in a variant way. While this is good, as I mentioned, I want to store the results of the processing in a table. So I have created a task to insert the data of processed from the PDF into a table and then send a notification to Slack. Now, as part of that, I'm doing two things. For inserting, I'm looking at the stream to see if the stream has data. And if the stream has data, then doing the insert part. And once the data has been inserted into a table, then I'm calling this function called Slack message. As I mentioned, the Slack message is using the external access feature, where as an admin, I created a network rule to connect to the Slack endpoint. And as part of connecting to the Slack endpoint, we can now call this user-defined function and send the appropriate message. So let's see all of this in an end-to-end manner. Once the data has been inserted into a table, I can run a simple query like this, where I can see how many people have recommended this product board. So right now you see 3 people, and I'm going to have a new PDF file where I will upload this to the stage and then process it. Now, in this case, there is a new user, Sarah Johnson, that's recommending this product board. So let's go ahead and upload this file to the stage. Now, in this case, I'm using an internal stage. You could use an external stage or AS3 compatible storage as well. So let's go ahead and upload this file. And as the file is getting uploaded, let's go ahead and take a look at the streams to see if it has detected the new file. Now, as we see here, it did detect that a new file has been inserted. So as this is being inserted, it will then kick off the task that will kick off the PDF parse function to start the processing of the file. So if we go back to this task, PDF ingest, it looks for if the stream has data, and then based on that calls this function parse PDF parse. Now, if we go back to my task section in Snowsight, you would be able to see the different jobs that have been run as part of this task. While this is in progress, I also want to show you my my Slack notification, where I would be able to see a notification as soon as the pipeline is successful or failed. So let's keep this here and then refresh the task history. While this is opening, I also wanted to show you the orchestration that is happening behind the scenes, where I was able to create the task where the first one is to refresh the PDF stage and the second one is to ingest the PDF. So let's go here and take a look at the task history and look for and wait for the pipeline notification. So this shows that the task was actually succeeded, and we got a pipeline successful notification at this time. So now if we go back to my PDF processing SQL query, where I got 3 responses for the people who recommended, and run this query, now I can see that the user, Sarah Johnson, is also shown in my result. So to recap, we did 3 things. First, we created tasks and streams to orchestrate the end-to-end pipeline for processing new files as they arrive. Second, we created a Snowpark user-defined function to process the PDF file using PyPDF function. And third, we use Snowpark external access to send the notification to Slack as the pipeline completed. With that, thank you very much.
Hi, everyone. My name is Chenyi Ding. I'm a product manager at Snowflake. Today, I'm going to talk about data warehouse improvements. So the Snowflake engine supports multiple data formats, data sources, and data integration tools so that customers can easily store, process, and manage their data to make informed business decisions. Our team continues to drive improvements from both the performance and functionality perspectives so that our customers can run better and more efficient queries. In terms of performance improvements, we are introducing automatic clustering cost estimation private preview. Automatic clustering is a service in Snowflake that continuously clusters tables as needed to optimize query performance. In this private preview, we're adding a new function to help customers estimate both upfront and ongoing maintenance costs for this clustering service on a specific table. We are introducing the GA of materialized view maintenance efficiency improvement, where we've made the compute that handles materialized views maintenance more efficiently, which ultimately translates into cost savings for customers by more than 50%. We have also enabled insert support for Query Acceleration Services private preview. Query Acceleration Services provides a burst of compute to aid performance for unpredictable workloads like ad hoc analytics and queries with large scans and selective filters. With this private preview, insert statements are now eligible queries for the Query Acceleration Service, which will help make these queries faster and reduce the overall query cost. Top K pruning enhancements for order by and limit queries will be GA soon. Top K is a common type of query that have both order by and limit clauses. We have further improved the performance of these kind of queries. This improvement will be GA soon and automatically applied to any queries that will benefit from it. Lastly, result cache for certain non-deterministic functions is going to be GA. We've enabled result cache for certain non-deterministic functions like any value, max by, and min by, where even though the results might be non-deterministic, they are cacheable. Besides the lots of great stuff to improve performance and reduce costs, now let's talk about how we're simplifying and expanding what's possible with SQL for analytics. First off, we're making time series analysis much easier with as-of joins in private preview soon. This type of join allows you to easily join tables based on values that are not exactly matches, but rather approximated by the nearest preceding or following record. We'll see a demo of this in a moment. We're also introducing two new select star keywords, I like and replace, which allows you to select all columns using case-insensitive searching and replace certain expressions while preserving the column order. We're introducing a private preview soon to increase the size limit of the objects Snowflake can process. We're working on increasing the size limit of loading individual objects from 16 megabytes to 128 megabytes, which is commonly needed for use cases like machine learning and geospatial, where large objects are expected. Lastly, we've brought more flexibility in array manipulation with 4 more functions. Array generate range, which generates an array based on the start, stop, and step. Array sort, which sorts array elements in ascending or descending orders. Array max and array mean, which return the maximum and the minimum non-null values from an input array. So here is what we're going to see in this demo. We're going to simulate a stock trading scenario where I have a trade table with a bunch of randomly generated symbols with their trade time and trade quantity, and a quote table with the same list of symbols and quote time and bidding and asking prices for each of the symbols. In this example, each trade is associated with roughly 20 quotes. Our job is to find out the most recent quote associated with each trade. Now let's check it out. All right, let's take a look at the demo. So as mentioned, we have prepared for 2 tables for this demo. One is the trade table, which has the trade time, symbol, trade quantity, and trade price. We also have a quote table with the same list of symbols and the quote time, quote quantity, bidding price, and asking price. So in order to find out the latest quote price associated with a trade, the traditional way of doing this is to using a window function, typically a lead function, to find out basically a period between a quote time and the next quote time. So this is exactly what it does. We're joining the trade table with the quote table, where it has everything from the quote table, and in addition, a lead column which takes the next timestamp of the quote time. And as a filter condition, it will be specified in such a way that the trade time is within the current quote time and the next quote time, so that fits into the window. That's how we select it back, and we can check the results. So about 15 seconds, we found out, okay, for this, for every symbol and every trade, we're able to find the latest quote associated with that. With the introduction of as of join, though, this type of query will be more concise and efficient. If you look at this, you're basically going to use the as of join keyword to join the trade table and the quote table with, instead of on, with a match condition with t.time, the trade time greater than or equal to the quote time. That's how easy the query looks like. And we're going to execute the query again, which will yield the same result. So after about 8 seconds, we're getting the results back, and you can see this is exactly the same results as a previous query, but faster and easier query writings. That's all I have for this demo. As you can see from as of joins and all these great features that I introduced previously, will continuously drive the performance and functionality features of the Snowflake Data Warehouse. Back to Scott.
That's all we have time for today. Thank you so much for tuning in to learn about all of these exciting new announcements. If you're interested in any of the private preview features covered today, please contact your Snowflake account manager to apply for access. And for public preview or generally available features, check out our release notes and documentation to learn more and get started.